recording this session. Basically, so I can record the lecture. And my plan is to upload it. So if I don't upload the stuff, please get on to me. There's so much stuff going on. We're looking at PowerPoint Chapter 3. All right. So today we're going to be talking about network protocols and communication. Okay. Correct. It does not want to work. Let me sync it up. There's a little button over here that you press, and it synchronizes with the Bluetooth transmitter. First, make sure it's on. That's weird, because not even the laser pointer is working. All right.
Did you turn it off and turn it back on?
Yes, I did. Yes. I got plenty of batteries, guys.
Sometimes, oh, no, it doesn't. I guess this wouldn't happen. I was about to say, sometimes we put the battery in wrong and won't do it.
And I did double check.
Yeah.
Yeah.
Because most of the time we put the battery in wrong and won't read it.
Yeah. Well, see, there's a little plus sign right there, and there's a little plus sign right there.
Yeah.
So, no, yeah. In fact, that was the first thing I checked.
Yeah.
Well, I should still be able to see the laser though, and I'm not seeing it. So, well, we're back to square one. All right, I'll deal with this later. All right, so we're going to talk about network protocols and communications. Okay, there's rules to communication. Do you guys know what the rules to communication are? You will learn, and when you see this, you will go, yes, I knew that. So, some of the fundamentals of communication is that you have a sender or a source, a destination or a receiver, and a channel or a medium. Donald, who's the source in our conversation right now?
You.
Exactly. Who's the receiver?
Me.
Us.
Okay. You guys, yes. So the same thing in network transmissions. When you send packets, when you send bits, whatever, you have a source, IP address, and a destination IP address, or whatever's being used. So you have a channel or media. Hey, you guys have seen that word before, right? Media.
Mm-hmm.
What is media?
Like the that runs through.
Exactly. What's the media in our conversation right now?
Voice between you and me.
Yeah, what's in between here?
Space.
Some waves.
Well, but there's air in between here, right? Because if there wasn't air, sound doesn't transmit through air, right? So there's air, okay? So that's the media. Same for wireless, right? All right. In my case, I'm talking. There's vibrations coming from my what are these things called? Yeah, from the larynx, exactly, from my voice box. There's vibrations, right? That your ears are picking up. So anyway, but there's rules to govern all methods of communication. I've got to look at this because I can't see it too well. So you have a message, you have a signal, you have a transmission media, you have a signal, which is at the receiver, and then you have a message that's received. Okay? Hey, what happens if you don't speak the same language I do?
And the message doesn't get across.
Just saying. That's something else, right? So, rules of establishment. So, you have to have a protocol, okay? And it's necessary for effective communication, okay? You have a message encoding, message formatting and encapsulation, message size, message timing, message delivery. And that's all part of the protocol. It's kind of like if everybody started talking in here, we wouldn't know who was saying what or what was being said, right? So, we have to have some rules, or what's called a protocol, okay? So protocol used in network communications is also defines the message encoding, what I just mentioned, the delivery options, the formatting or encapsulation, the message timing, and the message size. Just as in when we speak, okay, we've identified a sender and receiver, common language, because we said it has to be the same language, right? Speed and timing. Because if I talk real fast, can you understand what I'm saying?
Not.
Sometimes you can't, right? You say, whoa, 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 slow down, right? The delivery and then a confirmation of the knowledge. Did you understand what I was saying?
Yes, sir.
We just communicated. Very good. So encoding, message encoding. Encoding between hosts must be in appropriate format to the medium. What does that mean?
It has to be in the right format.
Exactly as that. For the medium, okay? An access point has to have a specific frequency, right? The voltage levels on a cable need to be a certain voltage for it to be a 1 or a 0, right? So each bit is encoded into a pattern of sound, light waves, or electrical impulses depending on the network media. So it depends on the media itself, okay? The destination host receives and decodes a signal in order to interpret the message. So basically you put it out there, and wherever out there is, on the other side, it's received and interpreted. So message formatting and encapsulation. Encapsulation is a word you'll see a lot. What do you think encapsulation is?
It literally encapsulates the data so
Landon, what does encapsulation mean to you? Yeah, exactly. What about you, Michael? Same thing?
Yeah, put inside something.
Donald, huh?
It's put inside something.
Exactly. Encapsulation, yeah.
yeah, pretty much it compresses. Get through.
Well, I think I'll stick with the capsule, okay? Put it inside something. Put an end on each side, maybe, okay?
Yeah.
So there's an agreed format for letters and addressing letters, which are required for proper delivery, right? We put the letter in the addressed envelope, and that's called encapsulation. We put it inside the envelope, right? And then each computer, okay, there's an encapsulated in a specific format called a frame before it's sent over the network. A frame acts like an envelope, providing a destination, source, and address. If you notice, you've got a destination, here's the frame addressing, here's the encapsulated message, and then here's an end of frame, okay? The destination's got a physical hardware address, a source destination, and then a source physical hardware address, a start flag, a recipient destination identifier, a sender source identifier, an encapsulated data bit. So basically there's this formatted frame that's similar to putting an envelope or a letter inside an envelope. So when we talk, we break things up into smaller chunks. Because if I talk and I just keep talking and and I'll tell you that there's a bunch of chunks and they're all put together, you might lose the meaning of it. But when I take a long message and break it up into smaller pieces to travel around along the network, I pretty much A, know that I got the total piece. B, I know when it starts and stops, and it's not a big huge chunk, so I can do it a lot quicker basically. Each piece is sent in what's called a frame. Each frame has its own addressing information, like we showed in the previous slide. When it's being received, there may be a bunch of little pieces that are getting sent to the receiver from the sender. The receiver's got to put them together. Are they put together in any old order? So if I say this is the order of things, and you receive it as things order this is, your mind's got to put that together to be this is the order of things. So the same way packets have a numbering system or the frames, and it reconstructs it into the proper sequence. So there's also message timing, which is part of the rules. The access method, hosts on a network need to know when to begin sending a message, and how to respond if a collision occurs. Because if something else puts data on that wire, let's say, or on that network cable, there's going to be collision. And then we won't know which one of them was the right one. We have something that's also called flow control, which the source and destination hosts use the flow control to negotiate the correct timing to avoid the destination and ensure that information is received, to avoid overwhelming the destination. So it knows. It's kind of like a pacing. The response timeout, the host on the network has rules that specify how long to wait for responses and what action to take if a response timeout occurs. So there's rules. Rules for message timing. This is delivery options. And this you're going to see a lot. You might want to jot kind of this down, okay? And it's really rather simple when you think about it. But we've got one-to-one delivery, we've got one-to-many delivery, and we've got one-to-all delivery, okay? And we'll talk about unicast, multicast, and broadcast. We'll talk more about this here in a second, but that's what it looks like. Unicast is talking to one specific host. Multicast is talking to multiple hosts. And look at this. Broadcast talks to all of them. Okay? Learn that. That is definitely a good. Is everybody done maybe jotting down? Or I mean, it is if you're following along in the PowerPoint, so I'm going to go ahead and move along, okay? Network protocols and standards. So protocols are rules that govern communication, okay? Protocol suites are implemented by hosts and networking devices in software, hardware, or both. The important thing, I think, is that there's rules, okay? These protocols are viewed in terms of layers, and each higher layer or service is dependent on the functionality defined by the protocol shown in the lower levels. So it builds on itself. Remember we were talking about the OSI model and the layers? These are the layers that we're talking about here. Just think about it. If one layer doesn't understand what the layer below it is trying to put to it, it's pretty worthless, right? All right, so protocols and interaction is a communication between a web server, for instance, and a web client is an example of an interaction between several protocols. And you guys probably know this, but HTTP, an application protocol that governs the way a web server and the web client interact, right? You guys have typed it in, http://. You're actually defining the protocol. TCP is a transfer protocol that manages the individual conversations. IP encapsulates the TCP segments into packets, assigns the addresses, and delivers to the destination host. And Ethernet, what is Ethernet?
It pretty much allows communication over the physical network.
Exactly. It's the rules. It's the protocol that allows communication over dead link and physical transmission of data on the media network. It's not just the cable. You always say this is the Ethernet cable. Well, yeah, it's the Ethernet protocol cable. Okay. So, and remember that. We'll discuss that later on when it comes up again. So protocol suites and standards. A protocol suite is a set of protocols that work together to provide comprehensive network communication services. It may be specialized or specified by a standards organization or developed by a vendor. Okay, there's various different standards organizations or vendors. What's one vendor? Yeah, exactly. Cisco has their way of programming those switches. Juniper has a way to program their switches. HP might have their own way, okay? Now, because of that, vendors might be different, but the organizations that define the protocols that are used are out there too. Why do you think there'd be those?
Create like a whole, to kind of create some continuity.
Exactly. Continuity, yes.
Continuity, yeah.
Something that, okay, oye chicos, oye, si yo pongo a hablar contigo, ¿tú me entiendes a mí? Huh?
I did.
You did, right? Did you understand me?
I did.
You did, but you see what I'm saying? I established a different protocol. And those that knew the protocol or the language understood what I was saying. Good or bad or indifferent isn't the point, okay? But what I just meant was that, okay? So I can talk with him, but that's proprietary to us. See? That makes sense? Okay. So the TCP IP protocol suite is an open standard, okay? Hey, we can say English is an open standard. Yeah, tell that to the people in the north, tell that to the people in the south, tell that to the people in Georgia, right? Y'all? But you get where I'm coming from? There's still some changes, but yet we understand each other, but sometimes you can't. What are you saying? I need some ice. What do you want? The TCP/IP protocol suite is an open standard. The protocols are freely available, and any vendor is available to implement these protocols on their hardware or in their software. Do you think that's used a lot? Do you think TCP/IP is used a lot? Where? Oh man, that is the internet. Awesomeness. Yes, that is correct. But do you see why? You see why? The internet, can communicate so well with each other, right? So development of TCP/IP, Advanced Research Projects Agency, or ARPANET, was the predecessor of today's internet. ARPANET was funded by the U.S. Department of Defense for use by universities and research laboratories. And the first world, I don't know why they're talking about IPv6, the first World IPv6 Day, June 8th, 2011, many websites and internet service providers around the world, including Google, Facebook, and Yahoo, participated with more than 1,000 other companies for a worldwide trial of IPv6. I knew that, but that's why. Because those 1,000 companies tried out IPv6. And it was pretty successful. So the TCP/IP suite, protocol suite, has in these layers different things basically, okay? Like in the application layer, we got DNS, we got boot, we got DHCP, email, these are the types of emails, file transfer, FTP, web, HTTP, and then the transport layer uses UDP or TCP. UDP is unreliable transmission, whereas TCP is reliable. So if I use UDP, that means I send the packet out, and I don't care if it's received. I send the next one, and I send the next one, and I send the next one. You guys know of an example that uses that? You probably use it every day, actually. Streaming video. From YouTube goes using this, unreliable. If there's a disconnection in the network, it keeps sending it. It doesn't care. Sometimes you'll see an interruption, a pixelation. Okay? Whereas TCP says, hey, did you get it? You say, yes, I got it. Okay, here's the next piece. And it might be a lot quicker than just that. And then there's other different routing protocols like OSPF or EIGRP, which are routing protocols for Cisco switches and stuff. IP support uses ICMP, and there's IP and NAT, which is network address translation. So those right there kind of help in the network area of routing stuff around. And then our access router protocol, PPP, Ethernet, these are also protocols. So the TCP/IP communication process, when sending data from a web server to a client, the encapsulation procedure would follow like this. The web server prepares the hypertext markup language, or HTML page. The HTTP application layer protocol sends the data to the transport layer. The transport layer breaks the data into segments and identifies each. Next, the IP source and destination address are added, creating an IP packet. The Ethernet information is then added, creating an Ethernet frame or data link frame. This frame is delivered to the nearest router along the path towards the web client. Each router adds a new data link information before forwarding the packet. So it kind of scoots along, in a sense, by getting stuff added to it, taken off, encapsulation, decapsulation, until it gets to where it needs to go. This happens quickly, right? Real quick, real fast. So the TCP/IP communication process, when receiving the data link frames from the web server, the client processes and removes each protocol header in the opposite order which it was added. So it starts taking it apart. First, the Ethernet header is removed, then the IP header, then the transport layer header. Finally, the HTTP information is processed and sent to the where? To the web browser. And that's what you see on your quote-unquote web page. Here's some standards. ISOC promotes open development and evolution of internet use globally, or that's the Internet Society, okay? IAB, Internet Architecture Board, Management and Development of Internet Standards. IETF, Internet Engineering Task Force, develops, updates, and maintains Internet and TCP/IP technologies. Internet Research Task Force, or IRTF, focuses on long-term research related to Internet and TCP/IP protocols. ICANN, Internet Corporations for Assigned Names and Numbers, coordinate IP addresses, address locations, and management of domain names. And then IANA, or IANA, right? Internet Assigned Numbers Authority manages IP addresses, allocation, domain name management, and protocol identifiers for ICANN. So those two right there, and you have a domain name and an IP address that you can purchase perhaps from one of the vendors. But you can also see the drawing down there, how it kind of fits together. Electronics and Communication Standard Organization, the IEEE, or Institute of Electronic and Electronics Engineers, is dedicated to advancing technology, innovation, and creating standards in a wide area of industries, including networking. IEEE has a lot to do. EIA, Electronic Industries Alliance, standards related to electrical wiring, connectors, and network racks. You notice this right here, a verified Cat5e TIA EIA 568B. The colors on that wire, there's a specific order that those wires have, okay? And that's because that's standard. Even though you can have the colors in a different order, as long as it's the same order on the other side, it would work. But the standard would not be upheld if the colors change positions, because they're there for a reason. Telecommunications Industry Association, TIA, standards for radio equipment, cellular towers, voice over IP, or VoIP, devices and satellite communications. International Telecommunications Union, Telecommunications Standardization Sector, or ITU-T, standards for video compression, internet protocol, television or IPTV, and broadcast communications. Man, they got all sorts of standards, don't they? Again, why?
To create some continuity.
For continuity. So that, yes, so that the right hand knows what the left hand is doing, basically. Pardon me? Yes, consistency, yes. Yes. So here's some benefits of using a layered model, okay? The benefits of using a layered model include assisting in protocol design, since protocols at each level have defined functions. So you basically know how they're going to work. Fostering competition because products from different vendors can work together. Hey, I got a better router that we can use, and it follows these standards here. Preventing technology changes in one layer from affecting the other. And providing a common language to describe networking functions and capabilities. Again, what'd you say? Consistency?
Yes.
Exactly. Exactly. So the OSI model has got seven layers. The topmost is application layer, which contains protocols used to process communications. In other words, the programs that are running on your computer. Presentation provides the common representation of the data. Session provides services for the presentation layer to organize its dialogue and manage data exchange. Transport defines services of segments, transfer and reassemble the data. So it transfers it and reassembles it. Network provides services to exchange the individual pieces of data over the network between identified end devices. The data link layer provides methods for exchanging data frames between devices over a common media. And the physical layer describes the mechanical, electrical, functional, and procedural means to transmit bits across physical connections. Now, what would you think the physical layer is?
The routers.
Remember, routers and switches. Routers are layer 3. Switches are layer 2. What would you think? NIC? Yeah, the NIC. What about the cable that plugged into
Yeah,
the
the
NIC?
Ethernet cable.
That would be physical. Describes the mechanical, electrical, functional, and procedural means to transmit bits across physical connections. Did you say something?
No, I didn't.
Okay. Okay, the TCP/IP model was created in early 1970s for inter-network communications. Notice that there's 4 layers in this one, okay? This is just being presented so you know that it's there, okay? It's an open standard, or it's also called a TCP/IP model for the internet model. And if you notice, it's got the network layer, which controls the hardware devices and media that make up the network. It's got, excuse me, excuse me. It's got the internet layer, which determines the best path for the network. Hey, that sounds like routers and switches and stuff out there, doesn't it? And then the transport layer supports communications between various devices across a diverse network. Sounds like the connection between all these different networks. And then the application layer, doesn't that sound like the regular application layer we just talked about? It represents data to the users, plus encoding and dialogue control. Data transfer in the network. So we have what's called message segmentation. And it's basically large streams of data that are divided into smaller, more manageable pieces sent across the network. Look at this. Look at this. So I'm sitting there going, instead of it being one solid, path, it's broken up into chunks. Labeling provides encoding and assembly of the pieces when they arrive. And then multiple pieces are labeled for easy direction and reassembly. So by sending smaller pieces, many different conversations can be interleaved on the network, and it's called multiplexing. They all have labels, okay, because it's got to know how to put them back together. You think that they all arrive at the same time?
No.
You think they all take the same path?
No.
They might not. They might be delayed because there was a problem. And by the time that problem was resolved, they were sent somewhere else. That's taken maybe a little longer. But these other pieces already, in front of it, already got there. And the ones behind it are actually getting there even before these other pieces in the center. So when it gets to the end device, it has to put them together in the right order. So you have to label them. Well, so they are labeled. You don't have to label, they are labeled. So if part of the message fails to make it to the destination, only the missing pieces need to be transmitted. And there's another reason too. Hey, I didn't get piece 3 and 4 and 2. Send that, please. Okay? Unless it's UDP. This is talking about TCP, which is a guaranteed delivery, a reliable delivery. So protocol data units. As application data is passed down from the protocol stack, information is added to each level. This is known as encapsulation. We know the term, right? The form that makes data, the form that the data takes at each layer is known as a protocol data unit. So basically, if you look at the physical layer, which is the lowest layer, and it makes kind of sense, right? Bits, ones and zeros is all it is. Ones and zeros, bits. That's what comes out of the network card and goes to the cable. Frame, okay, the next one, it puts a frame together. That's done at a data layer. And then a packet assembles frames together. And then a segment assembles packets together. And then data at the application layer, which is where it reaches you on the desktop. If you look at this over here, I think it's got it on here. Probably did. Yeah. Bits, packets, frames. So there you go, bits, packets, frames. What was the other one? Segments. That's a transport layer, and you know what? I'm going to go ahead and put it up there. Right? At the transport layer. So segments. Segments? And if you notice, bits, frame, packet, segment, data. Notice as email data goes out, you got data, transport header on the data. Gets down to here, and then it has transport header, but also network header. And then it gets down here, and then it has transport header, network header, frame trailer, frame header. And then look at the bottom one, ones and zeros. Encapsulation example. The encapsulation process works from top to bottom. Data is divided into segments. The TCP segment is encapsulated in the IP packet. The IP packet is encapsulated in the Ethernet frame. Data, TCP segment in the IP packet. And that's what gets over there, here. Decapsulation, what's that?
It takes the data out of it.
The opposite, yeah.
Yes.
The decapsulation process works from the bottom to the top. Decapsulation is the process used by a receiving device to remove one or more of the protocol headers. The data is de-encapsulated as it moves up the stack towards the end user application. So it's basically backwards. Now, network layer source and destination addresses, which are responsible for delivering the IP packet from the original source to the final destination. Source IP address is the IP address of the sending device, the original source of the packet. So that's what it is. Where did it come from? That's the source. And see, that's a layer 3 IP packet, right? And hey, what about the destination? Where's this going? The IP address of the receiving device, the final destination of the packet. The final destination of the packet. Not the next place it's going, but the final place where it's going to go. The data link layer has the purpose of address is to deliver the data link frame from the network interface to another network interface on the same network. So on the same network, the data link layer is responsible for that. As the IP packet travels from the source to the destination, it is encapsulated in a new data link frame when it is forwarded by each router. So each router actually puts a chunk on it. This is L2 and L3, layer 2 and layer 3 headers, okay? Data access, devices on the same network. The network layer addresses or IP addresses indicate the original source and the final destination. The network portion, the leftmost part of the address, indicates the network the IP address is a member of. And then the host portion, which is the remaining part of the address, identifies a specific device on the network. See if we can see something. And that's true. Say the IP address is 192.168.1.10, okay? The network is the 192.168.1 coming from host 10, and it's going to host 9. Does it show it there? Yeah, it's going from host 10 to host 9. Okay. This right here, the destination, the source, and the destination what?
Yes.
The letters? What addresses though?
I'm sorry. MAC address.
Yeah, which is what, Donald? What is the MAC address?
Place it gets received at.
The place it's received, but the physical address.
It's assigned to a computer. It's hardwired. It's assigned to a device.
Yeah, the physical address of that network card is called the MAC address. Okay? Does that change ever?
No.
It doesn't. It doesn't, and that's what makes it key in all this. It never changes. Now, people have spoofed it, okay, or faked them, but technically it never changes. As opposed to what address? Which is constantly changing, right?
Yeah, especially when you.
Yes, exactly. Exactly. The data link frame, which uses MAC addressing, is sent directly to the receiving device. The source MAC addressing of the sending device, and the destination MAC address, the address of the receiver. So if we know that, boom, it's there. But guess what? The devices in between have to know where all those MAC addresses are. And that's easy on a network. Not so easy on the internet. Because you got 20 million routers and switches and lions and tigers and bears out there. Oh my. So devices on a remote network. Sending to a remote network, the source and destination IP address represents hosts on different networks. The data link frame cannot be sent directly to the network destination host. Therefore, the frame is sent to the default gateway nearest the router. So basically what that's saying is, hey, I don't know how to get it over there, but I bet this router that I send it to knows. At least it knows the next place to send it to, or the next place to send it to, before it goes to the server. The router removes the received layer 2 information and adds new data link information before forwarding it to us. What's the layer 2 information?
Oh, it's MAC address.
MAC address. What's layer 3 information?
The addresses?
That's why MAC addresses in a network work okay. And yeah, you could use IP addresses too. But the point is going out of this building, I don't know what any of those MAC addresses are. But I do know that the network that composes a bunch of different IP addresses is out on that other port over there, see? Because it's in a range, right? MAC addresses can be anything, even in here. So it doesn't know how to route them out there because it doesn't know. It'd have to know the hugeness of, I could have 20 million different MAC addresses with no rhyme or reason in another network. Okay. What'd you guys think about that? Mind-blowing. Okay, let me do this and let me shut the recording down.